There are ways to analyze differential equations qualitatively without obtaining an analytical solution to a differential equation. By analytical, we mean we have a function y of x, which we could write implicitly or explicitly, its dependence on x. And by qualitatively, I mean we could say important things about the behavior of the solution curves without obtaining that analytic solution. So one of the major things we could look at is what's called a direction field. So for the purposes of this section, let's assume that we could write our first order differential equation in normal form, okay? And so on the left-hand side, we have the expression dy dx, and on the right-hand side, we have some function of x, which is the independent variable, and y, the dependent variable. Y depends on x, okay? And so we have our differential equation in this form. Notice what this is telling you. On the left-hand side is a dy dx. What is that? That's the slope, okay? That's the slope of any solution curve with respect to x. And on the right gives us an expression for the slope. It might not be purely in terms of x, and it includes the dependent variable y in it, but nevertheless, if we look at the xy plane as this rectangle, and we treat x and y as both variables, we could still say something about the slope of the solutions, which eventually will depend on just x. So let's start with a basic definition here. In the equation that we see here, fxy, in here I write y of x, okay? It doesn't show up as y of x. I just wanted to explicitly make it clear that y, even though we treat it as an independent variable when looking at the slope function or the direction field, it's actually the dependent variable that we would like to solve, but because we haven't solved yet, we're just looking at qualitatively. So fxy is called the slope function or rate function, okay? The value of fxy that the function of f assigns to the point, to a given point, represents the slope of a line segment called a lineal element. So a picture is worth 1,000 words. And so let's get an idea of what this definition means. So evaluate the slope function of the differential equation that we see here at the point 2, 3. Okay, x is equal to 2, y equals 3, and sketch the lineal element at that point along with the solution curve there. So we have our differential equation. On the right, we have an expression for dy dx, and the slope function is identified with f, what's on the right-hand side, as 0.2xy. And we want to know the slope at the point 2, 3. Well, what do? We plug in 2 for x and 3 for y, and we get a slope of 1.2. And so the slope at the point 2, 3 is 1.2. Now, just to drive the point home here, some may be confused by what we're doing here and say, well, wait a second. I've calculated a lot of slopes of functions, and how I've done it is I have an expression y of x, okay, where on the left-hand side I have y, on the right-hand side I have x, and I learned all sorts of rules to take the derivative. For example, the derivative of x squared is 2x, and so on. But here, I'm using 2 different data points, 2 and 3. Isn't that kind of redundant? Well, if we do have a solution to this differential equation, okay, if we had a solution to this differential equation that ran through the point 2, 3, it would be redundant. All we would have to do is plug in x equals 2 into the solution, and it'll in fact give us that the solution at x equals 2 is 3. But again, the whole point of this section in direction fields is to say something qualitative about the differential equation prior to getting a solution. And even if we did have a solution, knowing how the direction field of it looks like for a differential equation will give us a much broader perspective of what's going on, the behavior at different intervals of solutions. And so if we were to draw this, if we were to represent this on a graph, so here's the point 2, 3, okay? And what I draw here in blue is what's called the lineal element. Okay, you just go to that point 2, 3, and you draw a line. Now, what's the slope of that line? The slope of that line is going to be 1.2. Okay, that's what the slope of this line will be. Okay, these values here I just chose to kind of give a slope of 1.2. Now, if we were to obtain a solution, and we could do so because this equation is what's called separable, which is something we'll talk about when we get to the analytical methods of solving differential equations, we would actually get that the exact solution explicitly is the expression that you see there. Okay, and if you were to plot that around the point 2, 3, you'll get this green curve. Okay, so that's the actual solution curve there. And notice what the lineal element does. It just runs tangent to the solution curve. Okay, so that's a remark. The lineal element runs tangent to the solution curve at the point. And here I just make a remark that basically we're learning qualitative things without even solving for the dependent variable y explicitly in terms of the independent variable x. We're treating them on the same footing when we're looking at direction fields. Now, the collection of lineal elements as slopes plotted on a rectangular grid representing the slope function at each point is called the direction field or slope field. Okay, so what that means is basically, okay, we just chose the point 2, 3. There's nothing special about that. We could have just chosen any random points here and plotted the slopes, okay, at different points, and we would get this vector field called the direction field of the differential equation. So let's go ahead and actually do that. Sketch the direction field of the differential equation that you see here near the origin. Sketch possible solution curves based on the direction field. Okay? So how do we do that? Well, we just go point by point. For example, say I wanted to know the direction field at the point, say 1, 1, which is like around here. Okay, so I have this dy dx is equal to fxy is equal to, of course, 0.2xy. And so f of 1, 1, which is the slope at the point 1, 1, is going to be 0.2 times 1 times 1. And so you get a slope of 0.2. And so you'll then you'll draw an arrow there with a slope of 0.2. If we chose, for example, say 4, 3, that point there, well, we could do that. So for the point 4, 3, we'll have dy dx at 4, 3 is equal to f at 4, 3 is equal to 0.2 times x, which is 4 here, and y is equal to 3. And we will get 2.4. Okay. So then we'll go to the point at 4, 3, which we said is around here, and we'll draw a slope, okay, of, we'll draw a lineal element, and we'll give it a direction. This is flowing to the right, and the slope of that lineal element will be 2.4. In doing this for many different points in the xy plane will give us the direction field that you see there. All right. And we're also told to sketch possible solution curves based on the direction field. Now, what do we know about each of these lineal elements, each of these vectors that we're drawing in the slope field or direction field? We know that they're tangent to the solution curve. Okay, so each of these vectors has to be tangent to a solution curve. So what we could do here is sketch this curve here in orange. Okay, and at each point there, the vectors are tangent to that direction field. Okay, to that solution curve. We could also draw just a straight line there. Okay. And these vectors, even though they're running along the solution curve, are still tangent, okay, because there's a constant solution there. And likewise, we could do this here and get the pink curve. The exact solution is this, okay, so we have a one parameter family of solutions to this differential equation, and we have C there as the parameter. And so you could see that these curves correspond to different possible C's, negative, 0, and positive. A final thing that I want to say about this direction field in particular is notice that when x and y are both positive, okay, which is over here, that our slopes are positive, okay? Likewise, when x and y are both negative, then x times y will be positive, and our slopes in the third quadrant are positive. On the other hand, if, say, x is negative and y is positive, which is the second quadrant there, you get a negative slope, and that's why you're seeing negative slopes here. And that also occurs when y is negative and x is positive, as you see in the fourth quadrant. Now, we don't have to just draw vectors randomly, okay? Just pick out points and draw the slope there, the lineal element at that point. We could do this formally. We could develop a method for actually doing this. And one method is the method of isoclines. So what is an isocline? The level curves of the slope function are called isoclines, okay? That is, for a differential equation that we see there, any member of the family of fxyc curves where c is a constant is called an isocline, okay? Sketching the vector field of a differential equation using isoclines is called the method of isoclines. And so what level curves are for functions of two variables are basically curves in the xy plane where that function's constant. Now, this function is what? It's the slope function. So what are we saying there? What is an isocline? An isocline is a curve in the xy plane where the slope is constant. If we draw the different curves, the different isoclines where the slope is constant, then we could get a methodical way of drawing this direction field. So let's do that. Sketch the isoclines, direction field, and solution curves of this differential equation that you see there. Y prime is equal to x plus y. Well, what are the isoclines? It's where the slope is constant. The slope here is x plus y, so we set it equal to an arbitrary constant, c. And if you just focus on x plus y equals c, you could solve for y. You get y is equal to negative x plus c. And now what you could do is choose different c's. Okay, so here c is equal to negative 4. Here c is equal to negative 2, c equals 0, c equals 2, c equals 4. Okay, so for example, this line here has c equals 0, or just it's the line y equals negative x. This line here has c equals 2, and it's the line y is equal to negative x plus 2. Okay, and similarly for c equals 4 and any c, actually. So all the isoclines here actually run parallel. Okay, and now why is that helpful? Well, what we'll do then is go along one of these isoclines. Okay, here c equals 0. So what does c equals 0 mean? It means the slope is 0 there. So what do? We just draw horizontal lines representing a 0 slope as we move down that particular isocline. Well, what about when c equals 2? Again, that means then that the slope equals 2 along the isocline with c equals 2. So what we'll do is go and draw vectors or linear elements that have a slope of 2. Likewise, we could do for 4 and negative 1, negative 4. So if you take a look here, negative 4, c equals negative 4, or this is the line y is equal to negative x minus 4. And when c equals negative 4, that means the slope of each of the vectors on this line will have a slope of negative 4. And so you could see that here we have vectors, each with a slope of negative 4. They're pointing down. And solution curves, okay, so we could solve this differential equation through a method called, for linear equations, first order linear equations, there's a method there, which of course we will learn. But for now, we just need to make sure that our solution curves run tangent to these vectors. And here you could see possible solution curves there, okay? So at this point here where the slope's going down, the solution curve is going to go down. Over here, it's going to be horizontal. Over here, it's going to go up, and so on and so forth. And so without even solving this, without knowing that this is indeed the solution curve, okay, or a one parameter family of solution curves, this c is different than this c. Okay, this is just another constant that you would get when solving this differential equation. So without even knowing that this is a one parameter family, we could have just guessed at how the solution curves look just by looking at the direction field that we obtained by the method of isoclines. And isoclines are lines in which the slope is constant for a differential equation.